All right, good morning, thank you. In this talk, I'm going to report some ongoing efforts to develop probabilistic tsunami design maps for the American Society of Civil Engineers for their upcoming ASCE 7 standards. So it's just some background. Right now, in the United States, there's no design criteria for any buildings or structures to resist the tsunami effects. And such a significant risk is normally ignored in the engineering design. So the ASCE Tsunami Loads and Effects Subcommittee is now developing a new chapter called Tsunami Loads and Effects for their 2016 edition of the ASCE 7 standards. So these new provisions will be specifically addressing the tsunami loads and effects on buildings. And they will also incorporate aspects of the performance based on tsunami engineering. The ASCE 7 standards will be applicable to the 5 Pacific states. The later updates will include Guam, American Samoa, and Puerto Rico. This Chapter 6 will become the first national tsunami design provisions establishing the standard that will be referenced later in the International International Building Code. And here is the list of the contents of this chapter. The stuff that I'm going to talk about today is mostly related to the section 6.6, inundation depths and the flow velocity based on run-up. So in the section 6.5, they propose 2 procedures to determine the inundation depths and the velocities at a site. The first procedure is called energy grade line method. This method will take a topographic transect from the shoreline to the point of run-up, and then use the run-up height and also the inundation depths, inundation distance as the target solution, and use a iterative process of energy method until they get match of the run-up and inundation distance. So these 2 quantities will be provided by the probabilistic tsunami design maps that I'm going to talk about today. So the second procedure is like a site-specific analysis, and you use offshore tsunami amplitude, wave period, and the waveform parameters as input for your 2D tsunami inundation model using a high-resolution DEM. I'm not going to talk about too much about the second one, but I will be focusing on the probabilistic tsunami design maps for the first procedure. So the project goes is that ASCE the structure member the criteria will be based on a 2,500 year maximum considered tsunami. So for the first step, we'll develop a probabilistic 2,500 year hazard map for the offshore tsunami amplitude at 100-meter depths. And then based on those offshore amplitudes, we'll develop the tsunami design zone for the 5 states for the use with the ASCE design provisions. And these maps will establish the national standards of the tsunami design loading on the buildings in the tsunami design zone. This is going to be a joint effort among University of Washington, NOAA, URS Corporation, and the ASCE. So we'll be producing the maps of the tsunami design zone for the 5 states. The coverage will be every part of the coastline for the 5 states. And within a month, we'll be submitting the maps for the ASCE main committee balloting, and by May of 2015, we'll finalize all maps to incorporate all the comments. So this slide shows the methodology that we're using to develop the tsunami design zone. So as a first step, Dr. Hunke, Thio, and his group at the URS has already just completed the 2,500 year offshore tsunami wave amplitude and wave period. And they also provide source disaggregation information of all those offshore amplitude. And those information will indicate what sources contribute the most to those offshore amplitudes. And then from those disaggregation information, then we'll be reconstruct the sources using a combination of PML-developed unit tsunami scenario sources based on the source location, rupture area, and also slip amount. So after we have some reconstructed sources, then we will be running the tsunami model to get the computed offshore tsunami amplitude, and then we will compare those at the locations where we have the PTHA values, and then we'll further adjust the model, adjust the source until we get satisfactory results with the comparison, and then we'll determine the source. After we determine the source, then we would use our high resolution tsunami inundation model to compute the tsunami flooding based on those offshore amplitude. So here are some examples of the 2,500-year offshore tsunami amplitude and wave period at 100-meter depths. You can see all the values are mapped over on Google Earth. When you zoom in, you can see two different kind of bars. The lower color bar, they indicate the offshore tsunami amplitude at 100-meter depths. And the brownish bars, they are the wave period. And for those color bars, on top of it, there is a circle that you can click on it, and then it will pop up with a window containing a table that you can get the information, longitude, latitude, tsunami amplitude, and also wave period. So after we get the source disaggregation information, then we'll be reconstructing the sources based on a database of 100 kilometer by 50 kilometer unit tsunami sources. And we developed a small tool that can determine the sources through a nonlinear least square method inversion between the model results and the PTHA values. And this is a step further than the source disaggregation information, and this will give us an idea what the source looks like and what the slip that we are dealing with. So after we determine, then we will go further to refine the those sources until we get a good agreement between the computer results with the PTHA results. So we have to satisfy basically at least two conditions. The errors between the computer results and PTHA should be less than 20%, and the model results should be greater than 80% of the PTHA values. So here are examples of the breakdown sources in the Cascadia for Washington, Oregon, and Northern California. And based on the PTHA analysis, this part of the coastline, the tsunami offshore amplitude are pretty much controlled by the local Cascadia sources. So on the right-hand side, you can see we divide the coastline into eight segments. For each segment, we come up with a source that can match, can get the best agreement between the offshore amplitude and computed results and the PTHA values. So on the left side is a combination of all eight segments putting together. You can see, although the results are not perfect, but they are pretty good agreement. So after we get the sources, and then we will use our inundation models to compute the sources, compute the tsunami design zone. So right now we come up with a total of 31 tsunami inundation models to compute to cover the entire coastline for the 5 states. Specifically for Alaska, we use 20 models to cover that coastline. It's a long coastline. So all those models will be computed at the current stage will be computed with 2 arcseconds and about 6-meter resolution. So here are some examples of the tsunami design zone maps that we finished so far. ASCE want to see those map products, including the inundation limit and run-up height, and display them on Google Earth. So these are the maps for ocean shores and the Westport, Washington. The source is plotted on the right-hand side. You can see the source, the slip is quite big, 25.9 meters. And the red shaded area are the tsunami design zone that we computed. And because they want to include the run-up height, so we have the dots around the inundation limit. So when you click on any dots, it will show you the longitude, latitude, and the run-up height. So this is the tsunami design zone for Seaside, Oregon, and these are the run-up heights that you can click on. And this is the Monterey Bay results, because Monterey Bay is not controlled by local sources. And the source disaggregation shows that the Monterey Bay inundation area is pretty much controlled by the Alaska sources. So we came up with source in eastern Alaska, and you can see the inundation zone, and this is zooming inundation and run-up heights. And this is example in Shemya, Alaska, and you can see how big the inundation is for this island for the 2005 year return event. And this is Honolulu, south shore of Oahu, and you can the disaggregation shows that the source should be coming from Aleutian Islands. These are the run-up heights. And what's interesting is to compare the tsunami design zone with the extreme tsunami evacuation zone that recently developed in Hawaii. On the bottom, you can see the orange color is the tsunami evacuation zone based on historical events, and the yellow area are the extreme tsunami evacuation zone recently developed in Hawaii. And you can see the two maps actually are very similar, and the tsunami design zone is slightly bigger than the extreme tsunami evacuation zone at some places. So here's the example of how you use the energy line method, and you can take a structure. This is Hilo Bay in Big Island. The white box is the structure, so you take a transect from normal to the shoreline and pass through the structure, and you take another two profiles plus minus 22.5 degrees, and then you do an energy grade line method along these three profiles, and then you can come up with the design value for your flow depths and flow velocities. So here's the progress that the maps that we've completed so far, and the next phase for us is to coordinate with NTHMP for map validation and comparison with the state inundation maps in 2015, and 2016. And then we'll develop maps for some reference sites with 10-meter grid resolution. Just for your information, here's the application time frame for the ASCE 7 standards. In the ASCE 7 standards, along with the probabilistic offshore amplitude and tsunami design zone maps, will come out in March of 2016. And as a national standard, the ASCE tsunami provisions will be referenced in the International Building Code in 2018. And the 5 states, the building codes will come out in 2020, and ASCE will be publishing a design guide in 2015 with several examples. Thank you. Okay, have questions? Yes.
Please repeat.
Oh, he's asking, is there any validation for the velocities? That's the difficulty for these maps, and that's why they prefer to use this energy grade line method, because they are more conservative. But I would, because in February next year, there's going to be a current velocity workshop. I hope we can get something from there. Thank you.